Time for us to do some practice with problems involving the second derivative. So also concavity, inflection points, maybe some second derivative tests thrown in for fun. As always, it's important that you're doing as much practice by yourself as you can, because that's how you develop your problem-solving skills. And the more that you do, the better your skills become. It's true for math. It's true for life. So keep practicing. And if you're following along with the videos, make use of that pause button and say, all right, let me see if I can do this next part. Pretty soon, you will. You're going to develop. You're going to become great at problem solving and being able to answer some of these questions. And hopefully, someday all of these questions. But for now, let's begin. So our first question today. Find the inflection points on the curve y equals 2x to the 6th minus 6x to the 5th minus 15x to the 4th plus 103x minus 83, and determine the intervals for which the function is concave up and concave down. Now we see the word inflection points. This is telling us automatically where we need to start looking. Inflection points deal with second derivative. So we know we're going to start by, hey, let's get the first derivative and then let's get the second derivative. So let's begin. Y prime would be 12x to the 5th minus 30 x to the 4th minus 60 x cubed plus 103. Okay. Now if we stopped here, you'd be like, this does not look promising, because it definitely does not look promising. We would be pretty much hopeless to try to find the critical points here, because we don't have tools to solve for a fifth degree, and there's no nice roots. But we're not doing first derivative. We're going to second derivative. All right, so second derivative, y double prime. That's equal to 60x to the 4th minus 120x cubed minus 180x squared. And the 103 goes away. It's nice. Now, we're looking for inflection points. Inflection points are where we change concavity. And usually that means is, where does the second derivative change sign? Because we can measure concavity by looking at the sign. So we need to look for places where it's undefined or where it's 0. Well, it's never undefined. It's a nice function, polynomial. So where is it 0? Well, for that, it'll be useful for us to factor. So let's see. Everything is divisible by 60. So let's pull that out. And then everything has at least an x squared. So we'll pull that out as well. So 60x squared times x squared minus 2x minus 3. And we say, well, can this factor? Well, it can. So that would be 60x squared times, and hopefully we're getting good at factoring. So the x squared would be x and x, and the 3, well, 3 and 1. And really the only thing that we have to think about here is it plus 3 or minus 3? Plus 1, minus 1? Well, they need to be different signs, and we need to end up with a negative 2. So it should be a minus 3 and a plus 1. Now, if we weren't sure, we would do our normal check. Okay, x squared, good. Minus 3x plus x, okay, minus 2x, minus 3. So, where are our potential inflection points? Now, you might notice I added the word potential, because it's not just where the second derivative is 0. See, where the second derivative is 0 is where one might happen, but it doesn't need to be where one does happen. So there's a distinction to be drawn there. So we say, all right, well, when could this equal 0? So we say, well, it could be x equals 0, or it could be x equals 3, or it could be at x equals negative 1. Now, what we'll do is we'll say, all right, we need to figure it out. Now, what we need to do is figure out what's happening to the second derivative away from these points. So we would say, well, let's draw ourselves a number line, and let's mark all these points. So we have, in order, we'd have negative 1, and 0, and 3. And now we can plug in. So it's very similar to when we talked about increasing and decreasing. see an increasing, decreasing. He said, well, let's just look at every interval and see what the sign is for the derivative. Same process. We look at every interval and ask the question, what's the sign for the second derivative? All right, well, what's a number below -1? -2, right? Well, let's see. We have 60, -2 squared. Actually, notice something here? That square, it's never going to be negative. So really, the 60 is already positive. It's this piece on the end. That's going to determine the behavior. So, we're going to plug in -2. -2 minus 3, negative. -2 plus 1, negative. A negative times a negative means that our second derivative is going to be positive. Okay, from -1 to 0, say like -1/2. Well, that'll be -3.5. That'll be +1/2. A negative and a positive means that our second derivative is negative. How about, say, over here, say, I don't know, 2. 2 minus 3 is negative. 2 plus 1 is positive. Still negative times a positive. The result is a negative value for the second derivative. And then way out here, 5, 6, 7, 8. Who do we appreciate? Mathematicians! Yeah! Mathematicians! Yeah! Oh, sorry. I got distracted there. All right. 5. 5 minus 3 is 2. 5 plus 1, 6. Positive. It's all positive. Very optimistic part of our function. So our second derivative is positive. Now, what can we see? Well, we're looking for where we change concavity. So, in other words, where we switch from being concave down to concave up. And if we were to mark, we could say, well, look, we're concave up because our second derivative is positive. Then we're concave down, and then down again, because these are where our second derivatives are negative, and back to up. So, where do we transition? All right, our answer is we have our inflection points are at -1 and +3. I was trying to put them together. No, they're separate. -1 and +3. And in particular, this is a case which emphasizes, hey, even though 0 was a place where our second derivative turned out to be 0, did not automatically make it a point of inflection. You have to check. It's not enough to say, hey, where is my derivative 0? And the real question is, what's happening to my second derivative on either side? That's what determines whether or not you have an inflection point. So always make sure to check. Now, in essence, what really ended up happening was because you see here this x squared. That means it was a double root. And because it's a double root, that won't cross. In other words, it's not going to change sign for the second derivative. Whenever you have an even root, so in other words, a root appearing an even number of times, then that's a place where whatever you're working with, your function, your derivative, your second derivative, it won't change. Whenever you have an odd root, so in a root that shows up an odd number of times, that's where you will have something changing sign. All right, good. Nice. Well, on to another problem. And it's kind of got a lot going on here. So we'll have to write small to fit it all in. So we're going to answer the following questions for the function f of x between -4 and 2. And we're going to use the graph to answer all these questions. Okay, now here's where we have to be careful. We are given f prime. So notice this function is not f. This is our derivative. So this is f prime. So we have to keep that in mind. So that we know the derivative, not the function, we know the derivative of the function. Our first task in part A, sketch f double prime. And we don't have to be very technical. So we just have to be like, well, close enough. Where close enough means we have the right basic shape. Okay, so what would we do? Well, let's mark a couple things here. And -4, -3, -2, -1, 1, 2. Okay, so I'll have my grid. I'm not going to worry about the vertical aspect. what I want to focus on is the sign and our zeros. So the second derivative is the derivative of the first derivative. So one of the things you want to do when you're first looking for what's going on is figure out, is there any place where our tangent line would be 0? So in other words, let's look at this curve here and ask ourselves the question, is there any place where there's a flat tangent line? A flat tangent line means that's the place where the derivative would be a 0. Well, it looks like there's 2. So staring at this, I see 2 places which have a flat tangent line, and they've even marked them for us. See, at -3 and at -1. So what does that tell us? Well, it tells us that when we go to the derivative, a flat tangent line means a place where we're going to cross the axis here. In other words, a place where the derivative would be 0. All right. Now, beyond that, we just need to think about what can we say about slopes. So we sort of eyeball the slopes in. So what do we have? Notice that if we draw a little tangent line here where we can use our pen, that's a negative slope. I'm going downhill. So below -3, so in other words, over in this stretch from -4 to -3, negative slope means I'm coming down from a negative value. Now, what happens from -3 to -1? Well, I'm 0. Then I do what? I'm positive slope. See? Positive. That's my tangent line. And then eventually I get back to 0 again. So what needs to happen? What needs to happen is I need to go positive and then head back to 0. Okay. So negative slope, positive slope. And what happens to the rest? Well, for the rest, I'm negative all the way, right? You can see there's my slopes. They're negative. They're going down. So going down. All right. In some way. All right. So there's a rough sketch of our f double prime of x. Okay, and that's pretty decent. Is it perfect? No. If we want it to be perfect, we'd spend more time saying, okay, what's happening to our slope? And what can we say? What's our behavior happening? But that's a pretty good notion of what the function is doing. Okay, so now we have our sketch of both f prime and f double prime. So we're ready to sort of plow through the rest of these questions. And there's a lot of questions here. So let's start with part B. Identify the intervals where f of x is increasing and decreasing. So how do we know if something is increasing or decreasing? Well, increasing, the way we look for it, if we have derivatives, and we do. So when we have derivatives, we say, well, that needs to be where our derivative, our first derivative, is positive, and we are decreasing where our first derivative is negative. So our justification is we look at the first derivative and check for the sign. Now, be careful. This can be easy to get confused on. I'm looking at the first derivative. I only care about the sign. So don't pay attention to whether I'm going up or down here. Just ask the question, where is the first derivative positive? Where is the first derivative negative? So the first derivative is positive where I'm above the axis. So I want to say which parts of the first derivative are above the axis. And the answer is, well, everything up to 1. So we can say we are increasing from -4 up to 1. And we can even throw in 1 if we wanted to. Now, why do I start at -4? Well, the problem asked me to go from -4 to 2. Where are we negative? In other words, where is the derivative negative? Because that's where we're decreasing. So I cover up the positive part. I want to be this piece right there. And so we are decreasing from 1 up to 2. Okay, that wasn't so bad. All right. Now, identify and classify the x-coordinate of any critical points of f of x. So where are we going to look for critical points? First off, there's no boundary because we are going from -4 to 2, but we're not including -4 and 2, so that's out. Our derivative is always defined. Because look, there's always points here. And therefore, that's out. So the critical points, well, that would be where our first derivative equals 0. And so I'm asking, when do I cross the axis here? When do I cross the x-axis? So that's here. So this is a critical point. Okay, so f prime equals 0 at x equals 1. So now we know there is one critical point, and it happens at 1. But what kind of critical point? So the way to figure that out is we ask ourselves the question, what's happening to the left? What's happening to the right? We check both sides. Now, to the left of our critical point, our derivative is positive. So what we really should be saying here is that this stretch here, this is where our function is increasing. So derivative positive means function is increasing. And this part, where our derivative is negative, that's our function is decreasing. This is just the same thing that we did in part B. I'm just adding it to this picture just to emphasize. So we're increasing, then we're decreasing. So we're going up, and then we're going down. Well, what goes up then down? A local max. So at x equals 1, we have a local max. Now, could we have done it another way? Yes. So here's another way we could do it. You see x equals 1, we know that's the place where the derivative is 0. If we did the second derivative test, we say, oh, in the second derivative, our second derivative at 1 is negative. The second derivative being negative means that our function has a local max. So that's something else we could do. So we'll say our justification, because we are supposed to justify. Well, we'll say since f double prime of 1 is negative. Okay, good. Now, part D. Well, the next thing we want to do is we want to identify where f of x is concave up and concave down. Now, concave up, this is where our second derivative is positive, and concave down, this is where our second derivative is negative. So now we switch to our second derivative. Come to this picture. Where are we positive? So where are we above the axis? Well, that's this little blip here. So we're concave up at, I should say 4, negative 3, less than or equal to x, less than or equal to negative 1. And then we're concave down at our other places. So from negative 4 up to negative 3, and from negative 1 up to 2. All right, good. So that's part D. All right, well, one more. Part E. Identify the x-coordinate of any inflection point. Okay, well, an inflection point corresponds to where we change concavity. And if you look at the picture, we're asking where does the second derivative change sign? From positive to negative, or negative to positive. And we could, of course, phrase it in this way. We could see, look, initially we're down, and then we're up, and then we're down again. So I'm writing down, this is our concavity. So where do we switch concavity? Well, at negative 3 and at negative 1. So the inflection point, we'll make a little side note here. This is concavity changes. And this happens at x equals negative 3 and negative 1. And there we go. There we go. Ah, wow. So we were able to extract a fair amount of information about our function by just looking at this graph and saying, hey, make sure we know how to read it. So this is one of those cases where you always have to make sure you know what graph you're looking at. It makes a lot of difference whether it's the function or the first derivative. And you have to say, okay, if I have the first derivative and then I want to know where it's increasing, decreasing. I just say, where am I above the axis? Where am I below the axis? If I want to know about concavity, I do something similar, but with the second derivative. So, all right, well, that's good. I think we squeezed it all on one page. All right, well, time for another problem. All right. Next problem. Find the two, there's two of them, inflection points for the function theta squared plus sine of 2 theta, where theta goes from 0 to pi. Also identify the intervals where the function is concave up and where the function is concave down. Okay, so again, we see inflection points. We know we're going to be doing second derivative. So what do? Well, we take two derivatives, right? So we have our function, our first derivative. Well, derivative of theta squared is 2 theta. Derivative of sine is positive cosine. And then we have to do the chain rule. So don't forget to multiply by the derivative of the inside, which is a 2. Now we go to our second derivative. Derivative of 2 theta is 2. I should point out, by the way, theta is our variable. I think it's clear from context, and it's okay that theta is our variable. We can have our variable be anything we want. It just depends on the problem. All right, back to our problem. Now, the 2 is going to float around. I'm not going to write it down yet because I suspect there's going to be more added to it. Derivative of cosine is negative sine. Remember, now sine, cosine, kind of tricky. Got somewhere around there's a negative coming in. Okay, so this is going to be a negative. Then a sine. Leave the inside alone. Then you need to, again, chain rule says multiply by a 2. There already was a 2, so their 2's combine to make 4. All right. Now, is this ever undefined? No. All right, that's good. So the next thing for us to do is say, when does this equal 0? All right, well, that's the same as saying for sine of 2 theta equals 2, which is the same as saying sine of 2 theta is 2/4, also known as a half. Good. Now, that's something we can work with. All right, so now we come to the question. When does sine of 2 theta equal a half? Well, okay, so to answer that question, we have to sort of think a little bit about a couple of things. So if we think about our trigonometry, if we think about it in terms of circles, so you draw your favorite unit circle. Let's say this is our unit circle. Now the sine is associated with the y values. So what I'm looking for is I'm looking for angles where the sine would be a half. So I'm looking for angles that look like that. All right. Now we have to be a little bit careful. I know we always have to be a little bit careful, but let's be a little bit careful. What do we know about theta? It can go between 0 and pi. So what's true about 2 theta? So 2 theta can go between twice of times 0 and twice times pi. 0 and 2 pi. So what I'm looking for is what can I plug into sine that produces a value of a half, where whatever I plug in has to be between the angles of 0 and 2 pi. Well, looking at the picture, it's like there's two candidates. There's this angle, and then there's that angle. Now, if I had a larger range of my theta, I might have been able to like wrap around and I'd get additional angles. But for right now, there's only 2, which is good because, hey, it says there's 2. So it's good that we have 2 candidates. Now, what are the angles? Well, this helps if you know a little bit of trig. It probably won't surprise you to find out they're not so bad. So, do you see that angle? Can you spot what it is? In the old days, we'd call it 30 degrees. But we're doing calculus now, so what do we call it? Pi 6. So, that says what we should put in should be pi 6. Now, be careful. Are we saying that theta is pi 6? No, We're not. What we're saying is that what we put in should be pi 6, and what we put in is twice theta. So twice theta should be pi 6, and then there's another angle, which is this angle here. Now, the way you can get that is think of going all the way to pi, and then go back pi 6. So pi minus pi 6 would give us 5 pi 6. Or, now let's solve for theta. Theta should be pi over 12 and 5 pi over 12. Okay, now we're in good shape. We've identified our points. So the next thing to do is to draw our line, which represents our domain. Now here, it actually has endpoints. So we have an angle 0 and pi, and then we found out pi 12ths and 5 pi 12ths. All right, so now we have two candidates. Well, we said there were going to be two inflection points, so they better be the inflection points. That's not enough, though. We can't just say, hey, we think there's two answers, here are two candidates, we're done. We've got to check. So when you're checking for whether things are inflection points, you ask the question, what's happening to concavity? So we need to plug in convenient angles. What's a convenient angle below pi 12ths? Well, 0 is below pi 12ths, and 0 is always convenient. Now you might say, wait, we can't plug in 0 because isn't that going to be a critical point or whatever we call it, potential inflection point? But we can. We're okay. Now, why are we okay? Well, because this is not coming from a problem with the second derivative, it's coming from the boundary. And if there's no problem with the second derivative, go ahead and use it. So in our case, plugging in to our expression, 2 minus 4 times 0 would be what? Well, it would be 2. So that tells us that our second derivative should be positive. So we start by being concave up. Now we go to our next interval. Our next interval is between pi 12ths and 5 pi 12ths. Well, what's halfway between pi 12ths and 5 pi 12ths? Well, it would be 3 pi 12ths, or also known as pi 4ths. So let's plug in pi 4ths. So 2 times pi 4ths would be pi halves. And sine of pi halves is 1. So you get 2 minus 4, which is negative 2, which is a negative value. So our second derivative here is negative. All right, so in other words, this tells us we're concave down. So I'll add some notes here. Concave down, concave up. From 5 pi 12ths to pi looks pretty good. Let's throw it in. We'll get sine of 2 pi, which is 0. Then we'll get 2 minus 0, which is 2. Which means it's positive at pi, so our second derivative is positive again. So we're back to being concave up. All right, now we have all our pieces in place. We know where our potential inflection points are. In fact, no longer are they potential, they are truly inflection points because we change behaviors up to down and down to up. So we're ready to write up our answers. So what do we need to do? We should say our inflection points, where are they? And they are at theta equals pi 12ths and 5 pi 12ths. And we are concave up, where we are from 0 up to pi over 12, and from 5 pi over 12 up to pi, and then we're concave down from pi over 12 up to 5 pi over 12. And there you go. Now you might say, wait, do we really include the equalities? It depends on who you ask. And I like to include the equalities because whenever we talk about things like concave up and concave down, we're really talking about how something is increasing or decreasing, which gets into behaviors of derivatives. So we're good to go. We're fine. All right, good. On to another problem. Okay. Ooh, interesting. We don't have a function. We have a chart. So what do we have? Well, we have an unknown function, h of x, which is f times g. And then we have a lot of information about f and g. And we want to use the table below to determine if any of the points at 0, 1, 2, 3 correspond to a critical point. And then we're going to use the information to figure out what kind of critical point. All right, well, so first off, critical points mean first derivative. So we should start by looking at the first derivative. That's the product of two functions. So first derivative shouldn't be too bad. So h prime of x, well, the derivative of the first times the second plus the first times the derivative of the second. All right, so far, so good. Now, it looks like all these have values, so there's no place where it's undefined. So we're going to be looking for places where we might get a 0 out. So let's work it through. So we have h prime of 0, h prime of 1, h prime of 2, h prime of 3. We have to check all of them because there might be several. All right, so let's start at 0. So what do we have? We're going to take f prime times g, so that's negative 2 times 1. So that's negative 2. And then we're going to take 0 times negative 1, f times g prime, plus 0. All right, negative 2. All right, 0 is not a critical point. All right, how about at 1? So f prime times g, 1 times 3, so that's 3 plus f times g prime, negative 8. All right, well, that's negative 5. That's out. Okay, how about 2? Maybe we won't have any critical points. All right, well, keep trying. 3 times 2 is 6 plus negative 1 times 6 is negative 6, which is 0. Ha ha ha, we found one. Woohoo! Okay, well, gotta check 3 as well. Okay, so 3, let's see, it'd be 1 times 1, which is 1, plus, and then here we have a 2 times a 3, f times g prime. So that's 6, and that adds to 7. All right, so we now know we have a critical point where our first derivative equals 0. There's one place. So a critical point at x equals 2. Nice. Now you might look at this and say, hey, look, below 2 we're decreasing, and above 2 we're increasing, right? Because we can say, hey, when I plug in 1, I got a negative derivative, and when I plugged in 3, I got a positive derivative. So it looks like we're going down, then up, and so, okay, first derivative test would say what? First derivative test would be saying x equals 2 would be down, then up. That would be local min, right? Good. Ha-ha. Well, that was easy. Huh. Wait a second. I thought we were supposed to do stuff with second derivative as well. Okay, let's do the second derivative test. Yeah, all right. Second derivative test. Good. Let's do that. Now, so to do the second derivative test says what? Well, first we have to take the second derivative. And so take the derivative of the derivative. You'd get f prime prime, because we're taking the derivative of the first times the second, then plus the first times the derivative of the second. Then we're going to add to that the derivative of the first times the second plus, oops, I ran out of space, plus the first times the derivative of the second. Now, you can simplify this a little bit. Namely, you see that these two middle terms are actually the same. So we can put them together. So this is f double prime of x times g of x plus 2 f prime of x g prime of x plus f of x g double prime of x. Now, second derivative test says plug in 2. Well, so h double prime of 2 would be f double prime of 2, that's two derivatives there, g of 2 plus 2 f prime of 2, g prime of 2, plus f of 2, g double prime of 2. All right, so let's work it out. So f double prime, we're at 2, times g of 2. So negative 12 times 2. Negative 12 times 2 would make that negative 24. Plus f prime of 2 times g prime of 2 would be 3 times 6 is 18. But we double that, so we're going to have 36. Plus, then we have f of 2 times g double prime of 2. So negative 1 times 15. So that's a minus 15. So negative 24 plus 36 minus 15. Well, if you add the first and last, that would be negative 39. 36 minus 39 means negative 3. Okay, so what's our conclusion? Well, second derivative is negative. That means we have a local max, right? Because the picture, a little way to remember, second derivative is negative. Our picture looks like that. So local max. Okay, so second derivative test says x equals 2 is a local max. Now, you might notice something here. We took both of these tests, right? And we said, hey, it's a local max. And over here we said, hey, it's a local min. It can't be both. You can't have something be a local max and a local min unless it were constant, but that's not the case here. Things are changing. All right, so what's going on? Now you might say, how do I know it's not a constant? Well, if it was a constant, the second derivative should be 0 at that point. So that's how I know it's not a constant. What's wrong? Which test should we believe? Should we believe the first derivative test or the second derivative test? And the answer is, this first derivative test we can't apply. It's not valid. Now, why can't we apply the first derivative test? Well, the problem is that even though we understand something that's happening, so we have 2, and we say, all right, well, let's look at 1, let's look at 3, we don't know if that's the right place to look. So 1 and 3 are far from 2 in some cases. The function could have had some critical points in the meantime in between. And when you're applying the first derivative test, you have to say, I have to be certain that whatever I plug in, there's not a critical point in between. And that's the problem. We don't know where the critical points are. So we can't actually apply the first derivative test unless we had that information. So that just tells us our first derivative test is not valid. Well, that's okay. We'll live with that. So we have our answer. It's a local max. Second derivative test is perfectly fine because I only have to look at the point and not at anything else. So this is a case that shows you sometimes there are cases where the second derivative test is better. It will give you a right answer, whereas if you applied the first derivative test carelessly, we might be misled. Well, we don't want to be misled. We always want to get the right answer. That's always our goal, right? We always want to be right. Okay, one more. So, here we go. Sketch the curve y equals x cubed minus 3x squared minus 9x plus 15. Well, all right. So this is our curve sketching. Now, when we're doing our curve sketching, sort of our big idea is we're going to do good connect the dots. So that's our focus, is let's figure out where are the dots and how do they connect. So when we talk about connect the dots, we want to look at the first and second derivatives. So let's begin. So y equals x cubed minus 3x squared minus 9x plus 15. So our first derivative, 3x squared minus 6x minus 9. All right, we've got it. Now, we'll also need our second derivative. Let's go ahead and just do it while we're in our taking derivatives mindset. 6x minus 6. Good. Now, one thing that we can see right away is that these are nice derivatives. There's no places where we have things which are undefined. There's no endpoints to worry about. And therefore, we really need to be focusing on when are things 0. So we're going to do them both. So when is the first derivative 0? When is the second derivative 0? So let's start with the first derivative. Now notice everything has a 3 in it, so I could go ahead and divide by 3. And if we do that, we get x squared minus 2x minus 3 equals 0. All right, well, let's factor. This would factor. Now, of course, we hope it factors, but, almost everything does factor. If it didn't, we'd do a quadratic formula, but factors as x minus 3, x plus 1. It's not so hard. You see, you can even check. X squared plus x minus 3x is minus 2x and minus 3. Good. All right, so that means there are critical points are at x equals 3 and x equals negative 1. Okay, so we should add it to our list of dots. So let's make a list of dots. So we have a 3 comma something and a negative 1 comma something. We'll figure out what goes here a little bit later on. Now, let's switch gears and do the second derivative. So we're going to do our second derivative and set that equal to 0. Well, it's not so hard. 6x minus 6 equals 0. We can rearrange, and that says, well, x equals 1. So that's an interesting place as well. All right, so there's 1 comma something. All right, well, let's figure out where these dots are. So these are the important points which we're going to use to help us plot our function. So 1 is probably the easiest to plug in. So when you're plugging in 1 to a polynomial, you're really adding the coefficients. 1, minus 3, minus 9, and plus 15. Well, that's 16 minus 12, which is 4. Okay, negative 1. Well, that's almost the coefficients, but what you have to do is you have to pay attention to your sign. So at negative 1, what do we have? We're going to have minus 1, minus 3, plus 9, plus 15, because the minus 1 is going to make these two terms flip their signs. So you get 24 minus 4, which would be 20. Okay, how about at 3? Well, 3 cubed, 27. 3 times 3 squared, 3 times 9, 27. 9 times 3, 27. Oh, lots of 27s here. Plus 15. Okay, that wasn't 27. All right, but you can cancel off 2 27s. Negative 27 plus 15 would give us negative 12. Okay, good. Now we're getting close. So we can start. We can draw a rough grid, and well, we can't do it exactly right, but like I said, we can get a rough grid here. So let's see, we're going to have, negative 1, 20. Let's just put that here. So this is at 20. And then at 1, 4, so that we can put here. So here's 4. And at 3, and negative 12. So there's negative 12. So here are our 3 dots. Okay, now we're almost ready to connect the dots, but we need one more thing to do, which is what we've really done here is we've chopped our picture up into 4 pieces, right? So it's like we've done the following. So we have what happens before negative 1, between negative 1 and positive 1, between 1 and 3, and after 3. And so I need to understand each one of those parts. And the way we understand it is what's happening to our first and second derivatives. So to do this, we're going to do a quick sketch here of our line. So we have negative 1, 1, and 3. And for each one of these, I want to know the sign for the first and second derivative. So here we go. Let's do the second derivative. And actually, the second derivative is pretty easy because we change our sign for the second derivative happens at 1. If I plug in something below 1, say 0, I'm going to get a negative. If I plug something above 1, say 2, I get a positive. So that tells me my second derivative is, got my sign wrong. It's negative below 1, and then it's positive after 1. All right, so there we go. Now, for our first derivative, well, it's a similar process in that we say, okay, we have our first derivative is really x minus 3 times x plus 1, and so we can test various points. If you plug in, say, negative 100, well, that negative 100 squared, that's going to be the dominant term. It's positive. So our derivative is positive initially. Then if we plug in, say, 0, we get negative 9. So then our derivative is negative, flip sign. If I plug in 2, it would be 12 minus 9. So it's still negative, which is right because our derivative shouldn't change sign at 1. Because 1 is something about the second derivative. It's not about the first derivative. And finally, if I plug in a big number, 100, the first term dominates again. So we're back to being positive. All right, so now what we've done is for each piece, we understand our first and second derivative. The reason that that's useful is it tells us our basic shape. So what do I mean? Well, here I want a place where the first derivative is positive, second derivative is negative. So that says our basic shape is something that looks like that. If we have a negative and a negative, well, concave down decreasing, our basic shape looks something like this. A negative and a positive says what? Well, we're decreasing but concave up, so we're going to look something like that as our basic shape. Positive says we're increasing concave up, so we're going to look something like that. So now I'm going to connect my dots here according to these basic shapes. I could do one other thing and just help remind myself that I know at the points where I have 3 and 1, I have a flat tangent line. At 4, I don't. Sorry, not at 4. At 1, comma 4, I don't. Okay, so here we go. Time to finish it up. So before negative 1, I'm this shape coming in. So something like that. From negative 1 to positive 1, I'm that shape roughly. So then I'm going to come down, and then I switch shapes. And so instead of being concave down, I'm now going to be concave up. And I'm going to come in at 0. And then after 3, again switching my shape, I'm going to do something like that. So something more or less, that's the curve. There you go. And certainly these points here, they are the interesting points where you have your max and min. We didn't have to plot like a million points and be like, okay, which one was the largest value? No, we found it using our derivative. It gave us information. Okay, good. Whew. All right, well, sketching the curve sounds complicated, but at the end of the day, it boils down to a few simple ideas. What are the interesting points? So is the first derivative and second derivative 0 or undefined? Where are those points actually in the plot? So you got to plot those points. And that's what we did here. Then what's the behavior of the first and second derivative between those points to give you the basic shapes, and then put it all together. It's a simple process, and with practice, as always, it gets better and easier. Okay, good. Well, thanks for coming. Have a good day.